Okay, so before I was giving you a quantum algorithm to compute dynamics, namely to solve the problem that I was posing at the beginning, that I call dynamics, that you're giving some easily to prepare state, some time, lattice, Hamiltonian, and observable and prescription for your error, and then you can do it in polynomial time in n, in t, and 1 over epsilon with a quantum computer, whereas with classical computers, we don't know how to do this in general. Now, so maybe let me mention that because I was asked during the coffee break. So if you don't have local interactions, so you don't have something like finite range interactions, this was one of the assumptions that I took at the beginning, then still is efficient as long as there are like a constant number of interactions. So meaning that the Hamiltonian is a polynomial sum of terms that have some Pauli interactions. So I think that this was already mentioned in the paper by Seth Loy. So it's much more general. However, the exponent of n and t will change in that time. So because when you do the trotterization, then you have to make sure that the error is continues being small, and this is why you'll have to do more trotter steps. And so this changes the scaling, but still polynomial. Okay, so I want to talk now about ground states. And so what I will do first is give you a general algorithm that is kind of simple to prepare to answer the question that I was telling you before, but this will scale exponentially in time, in n, sorry. The computational time scales exponentially in n. And the reason why it scales exponentially in n is that I'm not going to make any assumption, and we know that these kind of problems are QMA hard, so everything has to scale exponentially in n. So in that case, so people what are interested is in reducing the exponent, so keeping the generality, but having like the computational time is 2 to the alpha n, where alpha as small as possible. So here I will not try to get a very good alpha, just to give you some alpha, to see that it's, how this could be done in a quantum computer, even though the computational time, is exponential, so it will you will not get very far with that. So again, we have this Hamiltonian that is local on a regular lattice, so it could be now a non-regular lattice with no assumption for the moment. And then we want to compute is in the ground state some expectation value. And the way of doing that would be the same as we use for the dynamics, namely to prepare the state psi0, and once we have it, then to measure and then repeat it a number of times until we get the value with some prescribed error. So the question is how to produce state psi0. And so one way of doing that, and that's the algorithm, would be to take a random state. Take a random state, and for example, a random product state. And so if you write it in the energy eigenbasis, or in this basis that I defined before, then it will have a linear decomposition. And since this is a random state, the coefficients that you will have here will be of the order 1 divided by 2 to the n. Right? And so what you could do now is to measure this observable, and you just measure it once, and with a probability that is this one, then you will obtain the energy En. So what you can do is to do it once, measure, and just write down what is the E that you get, some number. Then you repeat it again and write it again. Actually, you don't have to write it. Only if in the second case is smaller than in the first case, then you just write down what is the energy that you get. and then you repeat it and repeat it and repeat it and repeat it. And if you repeat it of the order of 2 to the n times, then it's very likely that once of them you will get the ground state energy, so you will obtain the minimum of those. So you have to do it a number of times in such a way that you have a very high probability of having measured that. However, the problem is that maybe you obtain that at the third time, and since you're repeating and repeating and repeating, then you forgot the state. Well, but once you know how much is E0, then you repeat it and repeat it and repeat it, and then the next time that you get this E0, then you stop it, and the state after the measurement would be projected into the state E0. And now, so we call it E0 here, and then now you measure this quantity. Then you do it again until you obtain E0, and then you have it again. And so you see that the number of repetitions that you will have to do it will be exponential in n. The only question here that is a little bit more subtle is how to measure this quantity. And you see that you could say, well, let me measure them individually. So let me measure like h1 into some qubits, h2 in some other qubits. However, if these operators don't commute with each other, then the state in which you will project after obtaining the outcome will not be an eigenstate because they don't commute, and therefore this is not going to work. So you have to do it in a different way to measure this observable. But however, that's something that we know very well because there is a quantum algorithm that does precisely that, that measures this kind of quantity. This is the algorithm that is called phase estimation. So what you can do is to use phase estimation that I'll remind you in a second how it is, or what is the idea. And then with phase estimation, what you can do is really to measure this quantity, and therefore you can do what I told you before. Okay? So the idea is to prepare a random state and measure random state, measure random state, measure, and in order to measure, you use phase estimation. And so phase estimation, and the idea is that if you have like a unitary operator B, and you start with a state psi that is an eigenstate, the algorithm allows you to compute this phase. And so the idea, remind you, these are books in quantum computation. What you have is that you input here the state psi, then you have some auxiliary qubits where you're going to read off what is this phase, and you put some Hadamard in each of your ancillas. You say k of those. And now you start performing control V. So control V, then control V square, control V to the 4, and so on. So it's always control V to the power 2 times n, 2 to the n, sorry, 2 to the m, or to the k. And then at the end, you perform quantum Fourier transform. And if this is an eigenstate, you see that you're putting here e to the I phi, e to the I2 phi, e to the I4 phi, and so on. And you're putting these phases, and you do quantum Fourier transform. Then what you will get here is basically the digits of phi. So this you have here phi up to k digits. Let me write it k. And this also works with superpositions. So you don't start with an eigenstate, but you start with some phi, which is some Cn En. The phase estimation, what we'll do is that we'll just create the state phi, okay, prime, which will be some Cn En, and here this phi n, where what you have to do is to take e to the minus I h and something like that, and some constant here that I don't even write. But that's the standard method. So you just plug your random state here through the phase estimation, and then you just read this register, and this will give you this phase, and from the phase, I mean, you have to make sure that there are no 2 pi's and so on in order to get it what is here, what is the eigenvalue En, and with that, you do what I told you before, you will get a value of En, and with this En, you have to repeat it, and there are some details about these 2 pi's and so on, but that's relatively simple to go through that. Okay, so again, this is a quantum algorithm to answer the question based on phase estimation, and if you look at what is the time that it requires to do, just by taking into account everything, so the phase estimation and so on, then you see that this scales like 2 to the power 2n. Now you can improve it a little bit, because when you want to measure this En, instead of repeating, since you're interested in getting what is the E0, then you can do amplitude amplification, and this amplitude amplification will accelerate it a little bit, so you get a better exponent, but still will be exponential. Okay, so with the standard tools, then one would be able to, run this algorithm, and notice that the only thing that is required here is to be able to do control e to the minus IH with some constant here, some t. So this algorithm uses as a subroutine the dynamical algorithm that we were using before. Okay, so I repeat that. In order to use this algorithm to get what is this expectation value, then you'll have to repeat the procedures an exponential number of times, and every time the procedure would correspond to taking a random state, now evolving now with the algorithm that we used before, controlled with a qubit, okay, which we can do, but totalization exactly the same as before, but now there is an extra qubit which is controlling that, and you do it these all times, and then quantum Fourier transform, then we know how to do that, and then measuring, repeating measurement, and this will produce the ground state after an exponential number of times, and with the ground state you measure the quantity. So I'm not spending too much time with that, because this is exponential in time, so this is not very useful, but at least this is an algorithm that works for that quantity. So I want to introduce some other algorithms that are much more efficient. However, now they don't apply to arbitrary Hamiltonians. They apply to Hamiltonians in which you have a promise. And this promise is that you have a gap, and the gap scales like 1 divided by poly n, like I told you before. And so this is the adiabatic quantum algorithm. And so I will do it a little bit slower here. And so the idea is to connect the problem Hamiltonian that you want to solve. This is this h equal to sum of h lambda with some simple Hamiltonian, and I will now be more clear about what I mean by connect. Some Hamiltonian which is very simple, like, for example, sigma Cn. And let me call it H0, and let me call it H1. And if the qualitative idea is that if we have this Hamiltonian, it's very simple to prepare the ground state of this Hamiltonian. So this would be like, if I put say 1 is 0, this Hamiltonian, the ground state is 0 to power n. So then we can prepare this Hamiltonian, and now we would like to deform continuously this Hamiltonian into this Hamiltonian by changing the parameters in such a way that hopefully then this state evolves continuously to the ground state of this Hamiltonian, what we call E0, for example. And so the question is, so what is the time that it will take just to deform this Hamiltonian in such a way that this state follows and ends up this E0. And this is what the adiabatic algorithm does. Okay, so deforms your Hamiltonian. And now, in order to deduce, so if we manage to find that there is a deformation that will produce this state efficiently, what we will have to do is to evolve according to this time-dependent Hamiltonian, because now will depend in time. However, we saw before that the algorithm for dynamics also works for time-dependent Hamiltonian, so we can use the algorithm for the dynamics for this purpose as a subroutine, and then we will achieve the goal that we have. So now maybe a little bit more explicitly, so we have a Hamiltonian and we have a parameter, h, and the parameter is s goes between 0 and 1, and we have the condition that this Hamiltonian for h of 0 is h0, and for h is 1 is equal to h1. That's the condition. One way of doing that is to take 1 minus s h0 plus s h1. And so this Hamiltonian for s equals 0 is h0, and for s equal 1 is h1. So it connects these two Hamiltonians continuously. And now what we could do is to write the spectrum, so the eigenvalues of this Hamiltonian as a function of s between 0 and 1, and this is s. And so maybe there is the ground state is 0 of 0, and then there is 0 of 1, and so we have, all these 2 to the n will change as a function of your parameter. It will be a complete mess because we have an exponentially many eigenvalues in n, basically, in some n. This was of the order of n. So there will be many together. And so what happens is that we are lucky and there is no crossing here. So if the eigenstate corresponding, so the eigenvalue corresponding to the ground state as a function of s does not cross the first one, or if you want the gap, this is what we defined. The gap is always positive. So we could define gap as a function of s would be equal to E1 of s minus E0 of s is positive, strictly positive. Then the adiabatic algorithm tells us that by changing this parameter sufficiently slow, changing s as a function of time from 0 to 1 slow, and now we'll see what slow means, then if we start with the ground state of h0 and we deform the Hamiltonian slowly, then we will end up in the ground state of h1. So that's what it will be an adiabatic evolution, what we call an adiabatic evolution. So again, how we would do this in practice will be to take, for example, this Hamiltonian, prepare the ground state, which is simple, and now start changing the Hamiltonian as a function of time, sufficiently slow, and doing the dynamics with this time-dependent Hamiltonian. And if we simulate the dynamics with the trotterization that we used before, then you can take into account the errors and so on, and see that you will end up very close to this state. And so, including the errors and so on, then at the end you can make an error epsilon and so on, and so then this will work. So the question is, how slow is slow? And now, so people have figured out, so how slow has to be slow, and so there are theorems that tell you that the time it will require, it will scale with n, and will scale also with the gap and with the derivatives of this h of t. Now this was an h function of s, a function of t, so you take the derivative of h with respect of t, and the second derivatives. So there is a big formula saying that if t is larger than some function, let me write here, that depends on n, depends on some norms of derivatives. Well, maybe I write it like that. Derivatives, second derivatives of h, and 1 divided by something like the cube of the gap, where the gap now is defined delta is equal to the minimum with respect of S of delta of S, then you will be as close as you want to the ground state. Okay, so that's the formula that is important, that tells us that as long as you find a path such that there is no crossing between the ground state and the first excited state, that there is a gap, then the time that it will take you will depend on something. But I mean, the important thing is that this scales like n, because this is the norm of the Hamiltonian, and the Hamiltonian has n terms. So this scales like n, scales something like n, and like 1 divided by the gap to the cube. And therefore, as long as the gap decreases at most as poly n, so if delta is larger than 1 divided by poly n, then this time for the adiabatic algorithm will be polynomial. Okay, so I repeat again. So this adiabatic algorithm creates out of some ground state, the ground state that you want to produce, and then after that you do the measurements, repetitions, measurements, repetitions, until you get the expectation values. But the question is, how much does it take to come here? And the time scales like something like n, so things that are polynomial in n, and 1 divided by this gap to the cube. And so as long as the gap now may change as a function of n, doesn't change too fast, doesn't close too fast, so it closes at most as 1 divided by poly n, then this will prepare your ground state in polynomial time. And so now you can go to the drawing that I had before with the phase diagram, and I told you that in physics, in many of the problems that appear in physics, what we have are gap phases and phase transitions, that connect the phases. And as long that you can move when you're Hamiltonian from this one here, crossing phase transitions, and all these phase transitions are of this kind that I told you before, critical, in which the gap decreases like 1 over poly n, this will be efficient, and therefore this will be an efficient algorithm for that purpose. And so you take now problems like the Hubbard model or things like that. So it is believed, I don't know if it has been proven, but it's believed that all the transitions that will appear in the middle are critical, and therefore with the adiabatic algorithm you will be able to create the states and answer these questions. Whereas the fact that you have a gap that decreases 1 over poly n, as far as I know, doesn't help in classical algorithms, and all of them still are exponential. Of course, it would be very interesting, even more interesting than building a quantum simulator, to find a classical algorithm for which you have a gap fulfilling this promise, then this will give you the answer, right? But we don't know that. But still, this means that even for ground state problems, the quantum computers can help to solve problems that we don't know how to solve in classical computers, and some of the problems are relevant from the physics point of view. Okay, so now, as you probably know, this quantum adiabatic algorithm is an algorithm that can be used to solve some other problems that are not quantum many-body problems. So you have optimization problems, where you have a cost function that you want to optimize, that you want to maximize. Actually, you can always write it in terms of some Hamiltonian, maybe non-local, but also a Hamiltonian that has a few body interactions. You have a SAT, satisfiability problem, then you can rewrite it in the same way. And so people have proposed to use also the adiabatic algorithm in order to solve optimization problems. Now, the question there is that these problems are typically NP-hard, and this means that this gap for those problems will decrease like 1 divided by exponential in n. So the time will be exponential. And now it depends on what is the path that you take. So maybe there is some Hamiltonian for which the path closes, the path is such that the gap closes exponentially. And there is another Hamiltonian for which you have a path for which it closes only polynomially, in which case you would be able to solve it efficiently. Also, this optimization problem. However, it's, I think that is NP hard or something like that to find what is the Hamiltonian that has such a path. Of course, you may be lucky, and for some problems that with classical computer, classical annealing, this takes a long time. With a quantum computer, this will take a short time. But it may happen also that if you do now classical annealing, which you also do something similar, then you also find the path for which is faster than some other ones, and so there's not so clear advantage. So what makes different this problem here of quantum simulation of the ground state with respect to optimization problems is twofold. So, I mean, first of all, there is a quantum problem that we want to solve. So at the end, the ground state will be a superposition of, let's say, of an exponential number of coefficients, whereas in classical optimization problems, at the end, the solution is classical. It's just one configuration state, one state on the computational basis. And the second is that here we know that for physically relevant problems, we know that the gap fulfills this condition. And so therefore, there is a good hope that for solving ground state problems, a quantum computer, a quantum simulator, will help us with respect to what we have now at hand. So I wanted to mention also some other algorithm. This is the variational quantum eigensolver. It is also very popular. And the variational quantum eigensolver, so what you can do is to take a quantum circuit, and you start now with all your qubits in 0, and then you put here 2 qubit gates. And these 2 qubit gates, I mean, each of them depends on a finite number of parameters, let's say on 16 parameters or something like that. So you have certain parameters here, P1, P2, the different layers, Pn. And at the end, what you can do is to measure here the energy. So we can measure each of these quantities individually, then compute the expectation value by repeating it many times. So here we don't have a problem of like at the beginning. So you remember at the beginning, I told you that in this algorithm here, it's not, I mean, if you measure independently the terms in your Hamiltonian, you will not achieve your goal because they don't commute, and you would like to project it to an eigenstate of the total Hamiltonian, and if they don't commute, measuring them independently will not give you an eigenstate as a product, so that's not useful. However, if you want to compute the expectation value of the energy, then you can do it individually. So you can measure, I mean, repeat it once and measure maybe this expectation value of H1, repeat it many times, then you measure in another sequence H2 many times up to Hn, and then at the end you sum those expectation values. So this would be the expectation value of H that now depends on your parameters P1, P2 that you chose for your gates. If you now change the parameters and repeat it again, then the energy will change. So if you want, you start with certain parameters. Let me write here a P for all possible parameters. Then you start with some value of the parameters here, and this is the energy. And then you change the parameters, and then you can try to take the parameters in such a way that this goes down, goes down, goes down, goes down, and hopefully this ends up at the energy is 0. And if this is true, this means that you will have prepared now here, after you just optimize all these parameters, just by measuring and changing them, just with using gradients and so on, so what people know what to do with the systems, then you can find the optimal set of parameters in your quantum circuit in such a way that the state here has a minimal energy, and that's a variational principle. And with that state, you can measure now the expectation value. And if you're lucky, then you will end up in the ground state. And so what people figure out already very early on is that now what you could choose in particular for these 2 qubit gates, the ones that are used in the trotterization and the adiabatic algorithm. So at the end, when we are using this adiabatic algorithm and we change the Hamiltonian time dependently, then and you do the trotterization for this Hamiltonian, this will be some quantum circuit. So we know that if this circuit has a depth which is polynomial in n, then there exists one way of getting at least as good as the adiabatic algorithm. And therefore, if you do it now more general, so you start not just putting exactly the ones that corresponds to the adiabatic algorithm, maybe there is a shortcut for that. So maybe with a shorter circuit, then you could get into the ground state. That was the hope, and for some examples, this is shown. So this variational quantum algorithm, if you have enough number of parameters, it reproduces the adiabatic algorithm, but maybe it does better. However, this is itself, I mean, you're optimizing the expectation value of the energy is at least is an optimization problem. So you have to optimize a function of several parameters, and optimization problems are difficult classically. In classical, this is what you have to do it in a classical computer. So it may happen that to solve the problem, you have to solve a classical problem, which is very difficult, and you get the stack in local minima. There are these plateaus and so on, and so that's not so clear if you will get some advantage with respect to adiabatic algorithm. But nevertheless, so people now working with quantum computers and small quantum computers, they have implemented this variational quantum algorithm to solve some very simple quantum simulation problems, so 3 qubits, 4 qubits, 5 qubits. And for other problems, they have used this adiabatic quantum algorithm. So now maybe I make here a little break. So I mentioned this afternoon, that there is a problem in condensed matter physics that is very relevant, that is called the Hubbard model or Hubbard problem, in which you remember that what you have is a Hamiltonian consisting of fermions just in a lattice jumping from one place to another. And this problem is difficult with classical computers. Now, there is another version of the same model in which instead of fermions, you have boson. It's called the Bose-Hubbard model. So the Bose-Hubbard model is exactly the same Hamiltonian that I wrote you before, but instead, these operators A that I wrote, instead of having anti-commutation relations, they have commutation relations. And so this problem, actually, to find the ground state properties and so on, is something for which there is a classical algorithm that works very well. It's quantum Monte Carlo, it's called, this classical algorithm. So this has been solved already and is very well known what is the phase diagram for that system. But nevertheless, people in 2002 did an experiment with cold atoms in optical lattices, in which, in the modern language, what they were doing is a quantum simulation of that problem. So what they did is they take these atoms in optical lattice and engineer the interactions in such a way that they would correspond to the Hamiltonian of the Bose-Hubbard model, and then in the way they would like to know what was the ground state properties. So what they did is the adiabatic algorithm. So they were changing, they went to a region of the parameter space where the ground state, where the Hamiltonian is of this sort. Okay, it's a product state. It's very simple. They prepare the state, and then they would change in the parameters and observing as a function of the parameters how was the phase diagram, where were the phase transitions, and they observed that. Of course, this was not a quantum supremacy experiment because there is a classical algorithm that also gives you this answer, but it was very remarkable that already using this quantum adiabatic algorithm, it worked very well. And so I'll come back to that in the last minutes of my talk when I talk about analog quantum simulation. So, but I want to say is that this algorithm and this algorithm has been already used. The second one, let's say, in very small experiments with few qubits. I mean, I know that people have looked at some Hamiltonian in lattice gauge theories, some high energy physics, but with 3 qubits or 4 qubits, so it's still very small, such a way that they didn't see any problem with these plateaus and so on, because we have a very few number of parameters. And the variational quantum algorithm has been, the adiabatic quantum algorithm has been used in some of the experiments on analog quantum simulation with many atoms. In that experiment, there were 100,000 atoms, so it was a big system. However, I mean, of course, we don't consider it to be like a quantum supremacy experiment because there are other ways of doing that classically. And on top of that, the Hamiltonian had errors. It was not perfect. But I want to talk about the errors in quantum simulation at the end. So I think that I'll stop with the ground state here, and I will move to the thermostate. So if you have any question?
Do all these algorithms apply to simulating open systems as well?
Yes, so the dynamics, so the algorithm for dynamics, it applies to open systems. So you can, basically, the idea is that you have a master equation, well, you have a master equation. So if it's described in terms of a master equation, so Lindblad equation for the density operator, then what you can, is not a Hamiltonian evolution, but you can put ancillas that interact and then take them away, like in the trotterization. And this gives you the evolution corresponding to any Lindblad, as long as the Lindblad fulfills the same condition as the Hamiltonian, namely that the Lindblad can be written, or the terms of the Lindblad can be written in terms of some operators, and there are polynomial of them. So indeed, yeah, as long as you have a master equation, this can be simulated and is efficient for the dynamics. For the ground state, of course, the ground state is different. So the equivalent in an open quantum system is not the ground state of the Lindblad, it's the steady state of your system. And for the steady state of the system, I mean, that's, I think that, again, you have to use assumptions, because, so typically, you evolve with a Lindblad equation, you will reach the steady state, but nobody tells you that it will take a polynomial time. It may take an exponential time. So there are some theorems that prove, that tell you that under some conditions, it takes polynomial time, or even log time, even, and in those cases, it will work efficiently. But there are some problems for which these conditions are not fulfilled, and therefore we don't know if this will take polynomial time. Thank you.
Yeah, I have a question just to, on your right. Yeah.
Okay.
To be sure to understand the connection. What I understood is that you can efficiently found ground state given the fact you know the ground state of an easy Hamiltonian and you have this condition on the gap. That's one thing. The other thing is to estimate expectation value for well-motivated Hamiltonian, local, etc. The thing I didn't fully understand is the connection with the phase diagram, in the sense that in terms of interesting applications, we would like to draw phase diagram to see if we can have ambient temperature superconductor or this kind of things. So what is the exact connection between I can estimate an expectation value, I can construct this ground state and the phase diagram? This I didn't fully understand the connection.
Okay, so for the phase diagram, so in practice, so you have a couple of parameters in your Hamiltonian, let's say in the ground state, H and U, like I told you before. There would be one phase that is the trivial. So maybe when U is equal to 0, that's trivial. So all these states, we know what they are. And now what you can do is start. So this would correspond to Hamiltonians of this kind, part of the phase diagram. And now from here, you can deform adiabatically to other Hamiltonians in which this U is different than 0. And so you can just start from here and change adiabatically and make measurements. Okay, so again, so you would do the adiabatic quantum algorithm, measure some observable, repeat it, measure, and average. And this will be the value in, let's take 2 or 3 correlation functions and things like that. Then you do it, and then you explore in this direction. And then you may find some phase transition. So you will see that because the gap, gets very small. Okay, so your time requires, you require a longer time. But still, you will be able to cross this phase transition and enter this phase, because in this phase transition, if this is a critical system, then this gap will decrease as 1 over poly n. So it means that you can also explore some other phases that just by crossing phase transitions, as long as these phase transitions have a gap that decreases only as 1 over poly n.
Okay, so just to be sure, so the phase transition, there is always the gap that will vanish with a given law, which would like to be polynomial, at the phase transition. That's how it's defined somehow. The phase
right. Okay, so maybe I should have said that in all phase transitions, the gap closes.
Okay,
the gap closes. And so the question is, if you want to explore and go to some other phases that are, let's say, far from yours, if you have to close a phase transition, but if you have to close a phase transition, then if the gap only crosses like 1 over poly n, then you will be able to close it in polynomial time. And then explore this part of the phase diagram. And so what I said is that there are problems that are believed to be like that in physics, for which we cannot use at our advantage the fact that the gap is small in classical algorithm, but in quantum algorithms we would be able to do that.
Hello. I would like to know how are the adiabatic process implemented on the quantum computer? Is it decomposed into a series of unitaries? And in practice, how do we do that?
Okay, so in practice, So the adiabatic algorithm is nothing else but the dynamics with a time-dependent Hamiltonian. So what you have to do is to start with some Hamiltonian and change the parameters as a function of time. So what you would like to do is to start with some initial state and do the dynamics with respect or generated by a time-dependent Hamiltonian. And now the dynamics with respect to time-dependent and time-independent Hamiltonians can be performed with a quantum computer in terms of the trotterization. So what you will do is decompose this in terms of these 2-qubit gates, and in this way get that. And everything will be polynomial if the gap decreases like 1 over poly n. Now, for analog quantum simulators, this is what I will say at the end, then you will not do that. It's much more natural because the Hamiltonian is already the Hamiltonian of your system, so you just let the system, change maybe the parameters a little bit as a function of time, but without gates.
All right. I also have an adiabatic continuation question. So you told us that you can push through these phase transitions as long as they're sort of critical theories. But I was confused by this because you sort of say that the eigenstate, the ground state sort of follows along.
Yep.
But sometimes if you pass a phase transition, the number of degenerate ground states changes. So I'm wondering what happens if you
in
go
the thermodynamic limit. In the thermodynamic limit, if there is a finite n, it is still gapped, but the gap is very
then
small.
the gap exactly closes.
Exactly.
Yeah.
It only closes for critical systems. It only closes when n is equal to infinite. So for finite, there is a gap that scales like 1 over poly n.
But even then, for sort of the transverse field Ising model, if you go from like all the way transverse field, there's exactly one ground state. And then you go all the way to zero field, or even finite, and there's exactly two ground states.
Yes.
So at which one do you end up along that path, basically?
You mean with as a function of n or as a function?
Yeah, maybe as a function of n.
Yes. So what? I don't remember that one. So if I remember, if you are exactly at zero field, there is this degeneracy.
Yeah.
And before that, I don't remember how it opens up as a function of n. So, but it will happen if you come from the other side, then probably you will have is that when you come to this particular one, then with the probability 1/2 you end up with one, and with probability 1/2 will end up in the other one. So I haven't thought about that. But in the Ising model, there is a phase transition at a finite g, and this is a critical phase transition. So it means that you will be able to get there. What happens at zero, where there is an exact degeneracy? This I'm not sure.
Okay.
Hello. Hi, Professor. Thank you for the very insightful overview. So just now you mentioned that optimizing resources is very important in VQE and adiabatic. Like, you know what I'm saying. So I'm wondering, I'm from circuit synthesis, and we have developed very interesting tools for TOEFL plus HETMART circuit synthesis. However, we all know that circuit synthesis is inherently hard because the matrix dimension grows exponentially large as you have more qubits. So I'm curious, from a physicist's perspective, is it worth thinking about local optimization? For example, if I know how to work with 3-qubit TOEFL plus HETMART circuit, can I apply these methods into, for example, VQE? Or if not, what kind of restrictions do we have?
Okay, so I see that there are two approaches. That one of them is to do the adiabatic algorithm. In the adiabatic algorithm, if you have the conditions, will work for sure. And you could say, well, let's try to speed it up. And so you can just start for the adiabatic algorithm and then start going in the direction that you say with some TOEFLs and something and optimization and try to speed it up. And so maybe in this way you can speed it up. The other possibility is to say, well, I know that it works with the adiabatic algorithm. Let's forget about the adiabatic algorithm and try VQE and try to speed it up. And so this may work, but that's there is not a promise that this will work because we know that at some point when you grow your system, you may get stuck in some local minimum.
Okay, thank you.
Yep.
Hello, thank you for the talk. As a question, a notoriously difficult problem is known to be the fractional quantum Hall effect.
Yeah.
You know, phase diagram exists. It's not only compressible, incompressible liquid. And everything depends on the interaction, in principle, 1 over R. So is there any efficient quantum algorithm that would predict the phase and these
Yes,
properties.
for the fractional quantum Hall effect, I think that what I said would apply. Because for the fractional quantum Hall effect, I mean, there is, if you have the Laughlin wave function, it's very simple to, Monte Carlo, you can compute the expectation value. So the question is, you have a Hamiltonian, and then you want to find the ground state. And so I'm not sure if this has the sign problem, but probably you have some possible interaction. You can make the sign problem, and in that case, it would overcome that as long as, I mean, you have a critical transition. If you go there from a trivial phase with a critical transition, then it should work. Yeah, indeed. Okay, so I think that we will move on now to the next part, and so we can have some questions at the end. So, okay, so I want to talk now about thermal equilibrium. So that's like an extension of the previous statement that I told you before. So the idea would be, again, that you're given the Hamiltonian, you're giving some temperature, or what is equivalent, you're giving some beta, and you would like to compute some expectation value of some observable with this Gibbs state. That's one possibility. And again, so if you're with the, so if you're, you think about arbitrary Hamiltonians, so like non-translational invariant and whatever, and so the ones that are very general, then this problem is also QMA hard. And the reason is because it includes the zero temperature, and therefore you can, it's as difficult as the zero temperature because it's a particular value of that. So what one could expect is also, so maybe some, so what happens here if we take beta equals 0? So beta equals 0, this corresponds to infinite temperature, the limit where, remind you that beta is 1 over T. So if T is equal to infinite, then beta is equal to 0. So then this is e to the 0, which is the identity operator. So it's a completely polarized state. And therefore, the expectation values of any observable, let's say, Pauli operator, any products of Pauli operators, is all of them are 0, because it's just the trace of the operator. So we can compute it efficiently, classically and quantum mechanically. So one could expect is that as a function of the temperature, so you're going from infinite temperature, so from beta equals 0 to 0 temperature, then at some point, this will get difficult, and in general. And so there will be a transition in complexity as a function of the temperature. And so, for example, we know that if the temperature is of order 1, sorry, yeah, it's exactly of order 1, so let's say, if the beta is of order 1, so there is some value, some order 1 value, for which classically we can compute things efficiently. Okay, so there is something which is called series expansion that converges, and one can prove convergence for some values of beta. So we know that as a function of the temperature, so if we start decreasing the temperature, you can simulate it classically, and at some point it has to get in general difficult to do it classically. And so what may happen is that if you decrease even further the temperature, then at some point it will be difficult quantum mechanically. So there might be a gap between the classical and the quantum in general. And so I don't know if this is known or not known, but probably there is a gap in complexity, classical and quantum complexity, in this problem as a function of the temperature. So, however, again, so here we may be interested in some problems for which this Hamiltonian is special, and so there have been some ideas of how to solve this problem. Just let me give you some ones in which, again, they scale exponentially, and then let me tell you one that scale polynomially. However, I will change a little bit the problem, as I will mention. So what would be one possibility? Well, just take e to the minus beta h half and apply it to a set of maximally entangled states of systems with ancilla. So this means that you will have your lattice. Let me draw it in one dimension. This is your system. Then you put an ancilla, a copy of your system. And then you start with a state which is maximally entangled state between the system and your ancilla. So this is this state here, maybe N. And imagine that I apply this operator here. And so now we'll have some other state. It's not normalized. But let's compute what is the partial trace of that state with respect to the ancilla. And so you see that since we are not acting, so let's write it like that. So this is the trace with respect of A of e to the minus beta h half times identity times phi plus to the power n times e to the minus beta h half. And now, since this is acting on the system and on the ancilla, you can move the trace, but the partial trace of the maximal entangled state is proportional to the identity operator. So this is proportional to e to the minus beta h half times e to the minus beta h halves, and it's equal to e to the minus beta h. So you see that if you prepare this state with one ancilla, what you have is a purification of your Gibbs state. So a way of solving the problem that I mentioned before would be to prepare this purification. Now, right, so you can prepare this state, then just by measuring observables in your system, maybe I do it here. So if I have the state psi, and I measure the observable O on my system, and I don't do anything on my ancilla, this would be the same as just using this property as computing the trace e to the minus beta h times O. And if I divide, now if I would normalize my state, this would be exactly what I want to compute. So as long as you can prepare the state properly normalized, then the only thing that you have to do to solve the problem that I gave you before is to measure the observable on your system, just not measuring anything on your ancilla. Repeat it many times, and if you repeat it many times and you compute the average, then you will get the solution to your problem. So the problem is reduced to how to prepare the state properly normalized. And you see that this is not so easy, because you say, well, at the end, if it's not normalized, so probably what we can do some measurements or something in such a way that we have this state here, right? Because it's not a unitary operator what we have here. And so people have figured out how to do measurements in such a way that with certain probability, you have the outcome that is the state. However, the probability for this outcome is nothing else than the norm of this, but the norm of this. So this is the probability of success. Would be this, but this is equal to the trace of e to the minus beta h. And, well, you have to put the right numbers here and so on, so I'm doing very qualitatively, but this goes like e to the minus beta n, because h is of the same, and it has n terms, and therefore you see that all these methods in which you prepare this state probabilistically, all of them scale exponentially. The probability decreases exponentially with the system size, so this means that you will have to repeat an exponential number of times. And this is not strange because, as I mentioned, this is independent of the temperature, let's say, so this would work for all temperatures. And we know that for sufficiently low temperatures, this is QMA hard, so any quantum algorithm has to scale exponentially. So this is one of the algorithms. So I don't have time, and I don't know very well, so all these algorithms, how to prepare the state. So what I want to do is to tell you about some other algorithm that will do something a little bit different. And so it's a little bit tricky, and so I want to explain with a little bit more detail. And the idea is that, let me first do the following. Let me take the spectrum. Remember that we have the spectrum that goes from minus n and n. And then let me fix the energy, some energy here in the spectrum. And so what I'm going to do is that I'm going to take some eigenvectors around this energy, and I'm going to produce now the expectation value of my observable in terms of some density matrix which has these eigenvectors here. I will explain it a little more detail. So I will take now some rho. This will be delta. And so this rho of delta that depends on E. And so what I want to do is to show how I can compute the trace of delta of E, of a trace of rho of delta of E times this observable maybe divided by the trace of rho of delta of E. So this, for the people who know physics, is more related to what is called the microcanonical ensemble. So the limit when delta goes to 0, this would be to take one of the eigenstates and then to compute the expectation value of the observable with this eigenstate that has exactly that energy. But here I'm allowing to have some width with respect to these eigenstates. And so why? Because if I'm able to compute something like that, what I can do is that I can now multiply, maybe I do it like that. I can, integrate this energy, so I can compute something like the integral, maybe I write it like that, e to the minus beta e. Maybe I can also compute things like that, and then you can convince yourself where delta goes to 0, this would give me exactly what I'm after. So the trace of all e to the minus beta h divided by the trace of e to the minus beta h. So don't have time to show it, but basically, qualitatively, you see that what I'm doing here is that I would write in an eigenbasis this, then I will have the trace in this eigenbasis, and so this will give me basically what is the density of states that I have in some reason, and then I'm integrating with respect to all of them. So that's the motivation, but I will explain now what I mean more explicitly, that in order to compute this quantity, it will be enough to compute these quantities. And these quantities are difficult classically as well. However, quantum mechanically, I'll show you how you can compute these quantities. And then, I will not have time, but I will tell you then how to do that with Monte Carlo and to get rid of the sign problem in quantum Monte Carlo just by using a quantum computer as a subroutine. So that was the original idea, but I don't think that I will make it. But I want to explain that with a little bit detail. So I'm going to change the problem by some other problem that is also physically motivated, that is different. And if I solve this other problem, then I may be able to solve the problem that I wrote over there, which is related to the original problem, namely to compute things in thermal equilibrium. So the problem that I want to solve is the following. So I have my spectrum. And so this is the energy. Now, so these are the eigenvalues and so on, like I mentioned before, with this density of states. Now, I'm going to do the trick that I told you before. I'm going to divide everything by n. So now I define E by n, and I call it E. So in the physical jargon, you would say that this is the energy density. And so now it goes from -1 and 1. And then I'm going to fix here some value, E. I'll call it E1, for example. And the goal, and I'm going to fix now, the goal would be to take a state with this energy, so to find a state, psi, in such a way that the expectation value of the Hamiltonian of that state fulfill this condition, is equal to E1 times n. Okay, so I fix this energy density, and I would like to have that the energy of my system is basically corresponding to this energy density. That's the first condition. And I would like now to compute expectation values with this state with a prescribed error epsilon. But, of course, the fact that the expectation value is this value is not good enough because, for example, I could take a product state which has this expectation value. So what I would like to have is something like an eigenstate that has exactly this energy. This would correspond to the microcanonical ensemble. However, since this is a discrete spectrum, if I take a point and I say that I want to have an eigenstate with exactly this energy, this will not happen, zero measure, right? So this means that I'm going to give some width. So I'm going to now I'm going to impose that the variance of H, so I will call delta square, is prescribed. Okay, so again, what I'm giving you here is some energy density. I'm giving you some value of n. I'm giving you the Hamiltonian and the lattice. I'm giving you the observable. And I'm giving you some prescribed variance and some prescribed error. And what I'm asking to do is to take a state which has this mean energy, that has this variance or smaller, and compute with that state this O and epsilon. Okay, so that's the problem that I'm going to solve instead of the original one. And the idea is that this problem, if delta is sufficiently small, and I'll say in a second what I mean by sufficiently small, then it will give me something which is physically relevant. And also, if I solve this problem, then I can use the solution of this problem to address this canonical ensemble with an efficient algorithm. That's the goal. Okay? So drawn here, what I just gave you is some energy, and I told you that there is here some width that I prescribed, and I would like to just take a state that has this particular mean value of energy and the variance, which is sufficiently small, which is delta. So let's see what is trivial, what is not trivial here. So first of all, imagine that I gave you some energy, and I can find a product state which has exactly this energy. So let me first take the trivial case. I take a product state, we write P, in such a way that this has this energy E1 times N, and let me calculate what is the variance of any product state. So what I can do is that compute now P H square P minus P H P square. And you can, because of the arguments that I did all the time, if this H that are here, this contains all the possible H lambda prime. If there is no overlap, then this will cancel with this one here. And if there is an overlap, then they will not cancel. So this means that this variance, or this delta square, would be of the order of n. It means that delta for product state is the square root of n. Or, in other words, if the formulation of my problem that I gave you at the beginning, I gave you some energy in such a way that there is a product state with that mean energy, and delta is a square root of n, is trivial. I can do it with a classical computer. So when it starts getting more interesting is when delta is narrower and narrower and narrower. And now you can see how narrow. So it turns out that for physical problems, now fulfilling some hypothesis, which is called ETH hypothesis, if delta is 1 over poly n, then you can answer some questions at finite energies, not finite temperatures, which people consider interesting. So this means that in order to get something that will have some physical relevance in this particular problem, then you better be able to get a delta, which is over poly n. So the question is there a way of getting a quantum algorithm that gets this delta over 1 poly n in polynomial time? And I mean, this would be a problem independent of the thermal state that I mentioned before. It would be more like fixing the energy in the macrocanonical ensemble. And later on, so I will show very briefly because I will not have time, so how this can be pushed in order to solve this other problem that I mentioned before. So, see, I'm renormalizing a little bit while I'm speaking because I will have to decide what to explain and what to know in the last 20 minutes, because I wanted to talk a little bit about analog quantum simulation, and I see that I'm running out of time. Okay, I'll manage. Okay, so let me tell you what is the idea of this quantum algorithm. So again, it's a quantum algorithm that will prepare a state that has certain energy and that this is very narrow in energies. And so what is the idea? So the step number 1 would be prepare a state. So this is a quantum algorithm. Prepare a state with the mean energy, some state, let me call it P, with PHP equal to E1 times M. So that's the prescribed energy, but I'm not imposing that it has the right variance in energy. And so how can this be done? Well, I mean, you gave me some energy that is somewhere here. This is this E1 times M. And now I go to the algorithms that I presented before. So imagine that the energy is the lowest energy that you can give me, which would be the ground state energy. Well, if I can use the adiabatic algorithm that I had before to prepare it, then I will be able to prepare this energy. So I will have the state that has exactly the energy that you're asking me. So, but what happens now if the state that you ask me has a higher energy? Well, it's very simple to prepare, because if you can prepare the ground state, you can start flipping a little bit your qubits, and since this is a continuous parameter, you can go from the ground state energy to any energy continuously just by changing your spins with local operations. So this means that you will be able to prepare, so as long as the conditions that I told you before to prepare a ground state efficiently are fulfilled, will allow you to prepare a state at the prescribed energy. So maybe you're lucky and the energy that I give you is sufficiently high in such a way that there exists a product state and you can prepare the product state right away, and that's something you can do classically. But if not, you can always prepare the ground state and start increasing the energy continuously until you stop in the place that you want. Now, the problem is that this state will still have a variance or squared deviation, which would be this delta. And it will not be the delta, which would be much larger than delta. So this would be much larger than delta. So how do we reduce now the width? Well, the idea is to apply a filter operation. So you take your state, so this is 2, is to filter the state. And so the idea is to take your P state and then apply something, which I'm going to call some P delta at energy E, in such a way that what it does is that it gets something that is much narrower, and that is narrow with a width delta. And so what could this be? For example, I can put a Gaussian filter. I can just write e to the minus h minus e square divided by 2 delta square. And something like that will make a filter. So you have here, if you write it as a sum of CE times, or Cn times En, you see that this Gaussian, the energies that are far from E will be cancelled, and only the ones remaining around E will remain. And so, therefore, you will make this filter smaller and smaller and smaller. So you're able to apply this operator to that, then you're done. However, we have the same problem as what I told you before with the e to the minus beta h. This state is not normalized, and so this is not a unitary operator. So how do you apply a non-unitary operator to your state P? And the idea is what we could have done before, but you can do it here as well, is to write this. Well, first of all, to realize that an exponential is very similar to, so if you have a Gaussian, is very similar to a cosine to some power. So you can approximate this by cosine of h minus e divided by n to some power n squared divided by delta squared. It's very easy to convince yourself that if you have this filter, which is this Gaussian filter, it's a Gaussian function, if you want. So h is like your x, okay? So you plot it as a function of the variable h, that is a Gaussian centered at e, with delta. If you take the cosine will be something that will be like that, will be very big. But if you take the power, only when it's 1, it stays like 1, and otherwise it's getting very, very, very narrow. And so that actually has exactly, this filter has exactly the same effect as this filter here. So this is the first step, is that you realize that applying a Gaussian filter is the same that to apply a cosine filter. You take the right power, and then you can check that they match. So you do the Taylor expansion to second order, they have the same one, and that's enough in order to make sure that these filters will be indistinguishable from each other if you put them. And then the next step is to write the cosine with a binomial formula. So this is e to the minus I, h minus e divided by n plus, and so I divided by n here because we have to make sure that the cosine doesn't have an oscillation. It's only half oscillations on the spectrum, it has width n. So this is why I divided by n, and I had to put an n there. But anyway, so this is e to the I plus e to the minus e divided by n to the power divided by 2 to the power n squared divided by delta squared. And you see that it's a typical trick that we can use. Now we can expand this binomial, and this at the end will be, well, I will not write it because I don't have time, is the sum. There would be some binomial coefficients, okay, R, M, and then there are products of those. But product of those are just e to the minus IH. So there would be e to the minus IH, and now some M, and maybe n's and things like that, something like that. And then e to the minus I plus I e divided by n times m. And so now we have the evolution operator here. So this means that a filter, an operator that you want to apply to your state that is not a unitary, can be written with this kind of tricks as a sum of evolution operators. It's like a Fourier transform, basically what we're doing here. And once we have that, then this means, in practice, that if you would be able to do some superposition of evolutions with different times, then you will have something like that. So you'll have the state P would go to the sum of this, whatever, R over M, and I don't write here some times e to the minus I H M divided by N times the product state. So this is the state that you have, and this M, you see, will be from whatever, 0, and then this R, which is, this is not precise what I'm writing here, but this is what you have. So if you have some initial state that you can easily prepare, you can filter if you're able to produce linear superpositions of this state. How many linear superpositions? Well, poly n. And each of them is an evolution of a time which is also poly n. So now the question is, how do you, giving some state, create a linear superposition of different evolutions? And then one would say, well, let's put an ancilla, let's do some control dynamics. However, this, whenever you measure your ancilla, you may get signs here, and this will spoil your method. So the idea, the third step, is not to use and prepare a superposition of a state with different evolution times, but rather use time series. So this was developed at the beginning of 2000 in quantum algorithms, And the idea is to say, well, at the end, what do I want to compute? What I want to compute is in this, let me call it the state phi now. I want to compute phi times this O phi divided by phi phi. I mean, this is what I was asking the problem to some precision. But then I can put this in here and replace it in this formula. And so what you see is that at the end, what you have are sums over M1 and M2, going very fast. But anyway, P is e to the minus I h M1, then O e to the I h M2, maybe divided by N times P. And here something similar. Okay, and with that, that's all what I wanted. So if you didn't follow the details, doesn't matter. So what I'm saying is that the whole thing corresponds to preparing some state, forget about this filtering, and go to this formula. And then you see that what you have to do is to start with some initial state, evolve for some time, and here evolve for some other time, and compute these expectation values. And this we know how to do efficiently with quantum computers as long as we have the way of doing the dynamics. So with control dynamics, there are ways of computing all these quantities. And in the same way, you can compute these quantities. So at the end, you don't prepare any linear superposition. What you use your quantum computer is to compute these numbers. There are of the order of poly n of them. So you repeat the evolution, you measure. You repeat the evolution and measure. You compute all that. You compute that, you divide one by the other, and then you will get the result. And so what you can show is that in order to compute that, it takes so the computational time here is poly n1 divided by delta, n1 divided by epsilon. So indeed, this algorithm is polynomial in time, polynomial in 1 over delta, but I told you that the interesting delta is 1 divided by poly n, so it's everything polynomial in n. So in other words, in summary, so what I gave you here is an algorithm which solves the problem that I gave you at the beginning in polynomial time with a delta that is prescribed to be 1 over poly n, something that we don't know how to do classically. Now what you can do is to say, well, if I can do that, can I compute now canonical ensembles? Can I solve the original problem, like e to the minus beta h? And so what happens is, don't have time to say that, but what you can do is similar ideas in order to set up a Monte Carlo algorithm in which you produce product states. And now you know that the Monte Carlo algorithm is a metropolis algorithm, actually, that you choose some configuration, and it was product states, and with this configuration, then you flip one of the configurations and you accept it or not, and then you sample many times, and with this acceptance or not acceptance, you compute expectation values, and at the end you get the value that you're interested. And this method, if you use classical algorithms, this is what is called quantum Monte Carlo, has the well-known sign problem. And so what happens with that is that you can get rid of the sign problem, because the sign problem occurs whenever you want to compute the probability. So you want to sample, in order to accept one configuration or not, you have to compute what is the probability of the current configuration, the probability of the other configuration, and depending on the quotient, you accept it or not. And the problem is that you cannot compute this probability efficiently with a classical computer whenever there is a sign problem. If there is no sign problem, there is a way of doing it, but the sign problem does not allow you to compute that. However, this probability can be computed with this method, so this means that you can overcome the sign problem and then have a classical Monte Carlo assisted by a quantum computer which overcomes the sign problem. Anyway, so since I have 4 minutes or 7 minutes, I wanted to make some remarks about analog simulation and errors. So I think that so far the summary is that it seems that in problems that are on the one hand interesting from the physical point of view, and on the second hand, let's say, polynomial in a quantum computer, then it's possible to have some application or some quantum advantage, because in the ones that I was mentioning here, we don't know classical algorithms would achieve the same goal. Okay, so that's the main message. And these problems can be dynamic, zero temperature, finite energies. These are the algorithms, and there are many, many other ones. Now, what happens in practice? So imagine that now you go to your favorite, the wonderful IBM machine that is there, or the one in Google, or the one that is in PsiQuantum, whatever, the one you want. And then you do what I told you. So it means that you will go there and then say, well, for any of the algorithms, I need to do the trotterization, so I will have to do the dynamics. Because for the dynamics itself, for the ground state, and for this one, you see that all the time the dynamics is behind all these algorithms. And so then you will say, well, I do the trotterization, and so I'll have to evolve for certain times. At the end, that's case polynomial n, or something like that. However, now in these quantum computers, there are errors. And so if you want to trotterize, so every time that you do a gate with these digital quantum computers, there is some error. And in most of the implementations, the error that you make is independent of the gate that is, the size of the error is independent of the gate that you do. If you do a control NOT gate, you have an error. If you do a gate which is e to the minus I, some small angle time the generator or a control NOT gate, you have the same error. So by trotterizing, you're making many, 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 many gates, and therefore the number of errors is exploding. So the bigger your system is, then the more you have to trotterize, and therefore you propagate these errors. And if you start putting numbers, then you see that it's very hard to get any quantum supremacy with those systems. Of course, at some point it will come, but they may have to have error per gates, which is 10 to the minus 5 or 10 to the minus 6 or something like that. So this is because of the proliferation of errors, because you have to do more gates that you're spending in the trotterization. So, trotterization is poly n, whatever, but if you put numbers, then there are many of those, and then they scale and start propagating. So that's why there is another set of quantum computers, which are called analog quantum simulators, which don't have that problem, but have other problems. And however, these other problems are not so dangerous, at least from what I know. So the idea is that instead of building a quantum computer now with gates, being able to have a set of universal gates, so what you can do is to take a system, to put it on a lattice, and a real lattice, the one that you want to simulate, now to switch on the interaction between your particles that are in your system that obey the Hamiltonian that you want to simulate. For example, in the Hubbard model, you would take fermion systems, electrons or atoms, and then using external fields, then we know how to make them interact according to the Hamiltonians that we want to solve. And so in those systems, you prepare this initial state, and then you switch on these fields. There is no trotterization, there is a continuum. So they have this Hamiltonian, then you let it evolve, and then you count the time, and then after the time, then you measure. There is not this overhead of trotterization. Now, these systems, however, the Hamiltonian that they have in the experiments, that what they set up, you say, I want the Fermi-Hubbard Hamiltonian. Then they will take some parameters, and the Hamiltonian that they will have in practice will not be the ideal one. It's not only that it will be not the ideal one, but it's very far away from the ideal one. So maybe I want to write a formula to show what I mean, because I think that this is probably one of the most relevant things that I wanted to say today. So I'm talking about, analog quantum simulators. And so I'm saying that you take one of your favorite systems, can be cold atoms or electrons in quantum dots or whatever, and now you would like to have the Hamiltonian H. However, in practice, in your experiment, you have a Hamiltonian H prime, which will be equal to, and this was the sum of H lambda, which is equal to the same that H lambda, and now there is a mismatch, and now you have a sum of new lambdas here. So what happens in these experiments is that in each lattice size where the Hamiltonian has to act, there is an error. And a small error, so maybe this epsilon is, let's say, 10%. So you remember that this was normalized to 1. So maybe this is 0.1 in an experiment, or 0.01 or something like that. So this number is very small. However, you see, these operators are acting on each of your lattice size. So the norm of the error, so the norm of this operator that is here, is equal to epsilon times n, because there are n terms. So if you evolve with this Hamiltonian, you have some initial state, and you evolve with the Hamiltonian, and then you compare where e to the minus I h prime t acting on initial state, this state after a time t of the order of 1 over epsilon times n will be basically orthogonal. And so you would say that then with an analog quantum simulator, you will only be able to do simulations for times this case like 1 divided by epsilon times n, and therefore everything that I say, will not work, because this time will be nothing. However, that's not true. And so for that, you have to realize that the problem in quantum simulation, as I formulated at the beginning, was not to get the state. And I formulated very carefully, saying that the goal in quantum simulation is to have the expectation value of some local observable up to some error epsilon. No? This is how it was formulated. That's what is interesting from the point of view. And so it turns out that even if these states are orthogonal, they may still give the same expectation value, right? With an error that is very small, like 1 over n or 1 over n squared. And for some cases, that you can prove that. Indeed, you can prove that even if there is some error that is extensive, that is proportional to n, if you want to simulate for some time t, then the error that you will make will not be like n times t. It's just epsilon times t. Or if you're looking at the ground state and you want to compute the expectation value of some observable in the ground state, even if you use your adiabatic algorithm or whatever you want to do, even though the state is completely orthogonal, then you can get your expectation value of your observable not with an error epsilon times n, but with an error epsilon. So in other words, the fact that you have extensive errors here, that proportional to n, this n somehow is cancelled by the fact that you're looking at local observable. You don't want to have the whole many-body system, but you want to have is the local observable that is right. So for example, imagine that your state, the ideal state, a trivial example, is the state 0, 0, 0, 0. However, your quantum computer with error has a W state, which is 0, 0, 0, 0, 0, 1, plus all possible permutations. Well, if you measure what is sigma c here, this is equal to 1. If you measure how much is sigma c here, it would be 1 minus 1 divided by n. So even though these states are orthogonal, the local expectation values may be very good. And so that's what happens in some cases in quantum simulation. So that's why, even though in these experiments, these errors are extensive, are very big, you would be interested in the whole state, will be completely wrong, the state. Still, to answer the question that I was answering at the beginning, it's still possible to have it. And for me, something that is interesting, is not known, is to what extent this is general. So to what extent all the problems that we are interested in physics will be resistant with respect to these extensive errors, and so we will be able to simulate them with analog quantum simulator without any error correction and still get some answer that we cannot get with a classical computer. And I think that's a good time to finish. Yeah. Okay, thank you.